Okay, so let's do a little bit of review because it was a while ago. We did section 5.2, which was just introducing trig functions. And so just for some review, and we started talking about trigonometric functions. Oh, very exciting. My iPad is back in action. But what's bad is I lost all my notes from before, but that's okay. So from here, I'm actually going to steal something. This one, copy, steal it for later. Because these are the ones that we wrote out last day, but I don't want to write them out again. I posted a trigonometry part 2 handout on Moodle. I'll retroactively go back and do 5.1 and 5.2 as a handout just so you have them with these. So it'll have these things that I'm copying now. Okay. So we have these trig functions, and if we know the terminal point, xy, right, then the sine of t is going to be y, and the cos of t is going to be x, and then of course tan t is y over x. And notice that as soon as we have division, then we have to exclude some values of x in the domain. Right, x can't be 0, we can't divide by 0, where x is actually the cos of t and y is actually the sine of t. So these first two specifically are the ones that we're going to really use today. Okay. So we will use the fact that sine t equals y and cos t equals x in our work today. Right. So we'll use the other ones too, but let's see if I can kind of. There. Okay, so we'll use these other ones, but these are the main players, that sine t is y and cos t is x if we're working on the unit circle, right? And xy is the terminal point. Okie dokie. So then if sine t is y and cos t is x, right, then we can bump this down a little bit. Then the pxy, which is the terminal point, bump this over. The terminal point of t is going to be the pxy, which is actually going to be, if x is cos t, then y is sine t. Right, so we use this fact that cos t is x and sine t is the y. So then if I want to talk about the cosecant of t, right, cosecant of t is just 1 over y, but y is sine t. So that's how we get from here to the fundamental identities. So we've got these reciprocal identities, and these first 3, these are the ones we use to be able to calculate them on our calculator, right? Remember, our calculator only has sine and cosine and tangent buttons, so they often don't have cosecant, secant, and cotangent. So what we'll do here, we use these identities to calculate cosecant which is the CSC of t, secant, which is the SEC of t, and the cotangent, which is the COT of t. So we use these identities to calculate the cosecant, the secant, and the cotangent on our calculators. Since we only have cos, sine, and tan buttons. Okay. So we rewrite them in terms of sine and cosine. And then, of course, tangent, we can also rewrite in terms of just sine and cosine and cotangent. So we can rewrite all of these in terms of sine and cosine. We also talked about the Pythagorean identities. So these are identities in case we need to rewrite a function, and we can just kind of morph functions. So here, I'll just put a little star here. Use these identities to rewrite a trig function. Oops. So we did an example last day, and hopefully you were able to watch the video from last day and hopefully it made sense, where we rewrote, I think, a tangent function. I don't have those notes on my iPad, so I just have to rely on my memory. I think it was a tangent function of some sort, and we had to rewrite it in terms of cosecant or cosine. So you can kind of change the functions with these identities. Sine squared plus cos squared is a really common identity that we use. Even secant squared is tan squared plus 1 is really useful as well. So depending on what you're doing, there are a lot of things that we can do with these identities. Okay, so that's why we call them the fundamental identities. I should have brought in, I had an example that I wanted to show you, but maybe I'll save it for next day for the final exam review. Okie dokie. So that's kind of the end of, end of the review. Let's see here. We'll start in section 5.3. 5.3 is called it's the graphing part. Trigonometric graphs. Okay. So what I managed to do, managed to squeeze everything onto one page for each section. So I don't know, nice. Trigonometric graphs. Trigonometric graphs. Okay. So what we're going to do is we're going to start talking about, we're just going to talk about the graphs of sine and cosine. I don't emphasize the actual graphing that much, but there are some things that we need to be able to see in trig functions and just kind of have an understanding of what the graph would look like. So, but then we're going to confirm that using Desmos, right? So we can always graph trig functions and any sort of graphs in Desmos, and that's really useful just to be able to check your work, right? Okay, so first we'll talk about, sine and cosine. We say sine and cosine are periodic, right? Because if you are on the unit circle and you start at 1, 0, right? As long as you remember that the cos is x and the sine is the y, then as you move around the circle, right, you can figure out what the x and the y coordinates are at every point, right? And we even talked about some specific points, pi over 6, pi over 4, pi over 3, pi over 2. right? Those are our main cutoff points that we're interested in. And so we know as we move through the circle, we know what X and Y are at those points, right? So if we think about our unit circle here, nice. Then we have these cutoff points, pi over 6, pi over 4, pi over 3, and we know the x, y values at these points. Do you remember? Root 3 over 2 and 1/2, right? It's really worthwhile remembering these terminal points because they happen again just for positive values of x and y, positive and negative values of x and y. So root 3 over 2, 1/2, and then the pi over 3 is the opposite, 1/2 root 3 over 2, and pi over 4 is the easiest one, root 2 over 2, root 2 over 2. Okay. And then, of course, each of these cutoff points, the quarter way marks, here you start at 1, 0, 0, 1, negative 1, 0, 0, negative 1, right? So we know all these points. But we also talked about moving through the graph, right? In the second quadrant, your x is negative and your y is positive. Third quadrant, right? Your x is negative, your y is negative. Here, your x is positive, but your y is negative, right? But these points all stay the same. It's just whether x is positive or negative, and y is positive or negative. So here, right, cos of pi over 6, for example, is root 3 over 2. And the sine of pi over 6 is 1/2. Okay. So what happens is if we start here, which is what we usually do, right? If I move around and I move through the circle here, I know my angle would be 2 pi plus pi over 6 if I came back to this point, right? But now I've moved through the circle once, but the point I end up at is the same, right? So even for larger angles, right, we move through the same circle, right? Same circle, same points, and we just move around and around the circle. That's what makes sine and cosine periodic. So the functions sine and cosine have a period of 2 pi, meaning it takes a distance of 2 pi to move through an entire cycle. It takes a distance of 2 pi to move through an entire cycle. So in that 2 pi, right, we go through, so if we're just looking at the cosine, cosine goes from root 3 over 2 to root 2 over 2 to 1/2 to 0 to negative 1/2, negative root 2 over 2, negative root 3 over 2, so on and so forth. Right, and so what we get is this kind of cyclical graph. Okay. So what you can do is you can figure out, you can do little check-in points like we kind of did verbally there and say, okay, well, for the cosine, if I'm following just my x values around, if I start at a length of 0, if I move 0, these up here, the t's are going to be replaced with angles. So we'll start calling them angles, right? Even though we've been talking about them as if they're the distance on the circle, they are. But we'll get to that in 6.1, okay? But they are angles, okay? And they are distances, okay? So they're the same. So you've got 0. So if you go from 0, okay, so I haven't moved anything, then x is 1 and y is 0. So cos of 0 is 1, sine of 0 is 0. Okay. And then we cycle through. We haven't even included the pi over 4 check-in point. The table would get too big. That's okay. We've got the pi over 6, pi over 3, pi over 2. That's up here, right? So now I'm in the second quadrant. 2 pi over 3, 5 pi over 6, pi. 7 pi over 6, 4 pi over 3, 3 pi over 2. 5 pi over 3, 11 pi over 6, 2 pi. Okay. So that's going through one cycle at particular check-in points. So here, let's just highlight that, okay, well, this here is quadrant 1. This here is quadrant 2. Quadrant 3, and we can just check in quadrant 3, I know both my x's and y's must be negative. And look at that, all those values are negative, right? So we're just going through the unit circle, and then we would just go through it again. And here's quadrant 4. Okay. So here, we use these starting points often, right? Specifically that the sine of 0 is 0 and the cos of 0 is 1. Yeah. So this, you've probably seen the graphs of sine and cosine before. So let's talk about the graph of sine first.
Do we have to memorize the table above?
This table, no.
Okay.
Because if you move through, right, if you have these memorized, right, and these quarter way marks,
yes,
then you'll have all of them memorized already.
Okay.
Right? Because here, if it's over 3, 2 pi over 3, well, then we're over here. So the sine, which is your y, would be, so now this is just being flipped over here. So it's negative 1/2 root 3 over 2, negative 1/2 root 3 over 2. So you can kind of work through the circle with these ones that you know, and just kind of flip them. In fact, I've got a nice, easy graphic. Let's see here if I have it. You guys don't really need a formula sheet. I can post it if you want to, but here.
A
I'll
formula
paste
sheet
this
for
in.
the test, you said?
Yeah, because, well, I mean, you can have it if you want, but because you get to have all your notes and everything, you don't really need it.
Can you still at least please send the sheet as
You
well?
bet.
Thank you so much.
So here it is all written out, right? But here, if you just know these 3, then this pi over 3 flips over to 2 pi over 3, but the x is negative in quadrant 2. The y is still positive, right? X is negative, x is negative. Here, both x and y are negative. Here, x is positive and y is negative for all of these.
Yep.
But notice how you're just taking kind of this section and flipping it over here, flipping it here, and flipping it here.
Yep, just the negative on x and that y that they change.
Yeah, so that's why I say don't memorize this whole circle. Just memorize these. And then just remember, okay, x is negative, y is negative, and where that happens. Here, I'll erase all this mess there. I'll post those, I'll make a note to post them right after class. Post formula sheets, just in case you want to look through them, right? Might be nice to know what you would have on a typical test and what you'd have to memorize.
Yes, please. Thank you.
You bet. Okay, so just some more terminology. So this here, this distance that it takes for this snake to repeat itself. So this is what the sine and the cosine curve both look like. They're just kind of waving back and forth, back and forth. Sine of t, sine of 0 is 0, right? So sine is going to start at 0, right? And then cos of 0 is 1, which we'll see it starts up at 1 up here, and then it goes down, up, 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 down. Some terminology here. The height between the x-axis and the tallest point, the height here is called the amplitude. And it's going to be replicated on the bottom half as well, right? So that's what we call the amplitude. And then we're also going to talk about a horizontal shift. So what can happen is if we have a horizontal shift, then everything gets shifted to the right or to the left. But everything just kind of goes. So that's when it's useful to know where the starting point is, because if I shift that over to the left, for example, then everything shifts over that amount. Let's talk about the sine curve before we do anything else. Sorry, I said sine, but I meant cosine. So here the cosine starts, starts at 1, right? Instead of 0, 0, it starts at 0, 1. Let's not do that. That'll get confusing. Starts at y equals 1. Okay. So again, we've got this period of 2 pi, right? But it starts up here and it ends up here. Okay. So that's how you know you've completed a full cycle. Whereas up here, right, it started down here. And even though we cross at the same point here, it's a little bit weird because we haven't done the bottom half, right? So here, then it starts going up again, right? And that's when it starts over. Okay, good. So what do these shifted sine and cosine curves look like? And how do we get some of this information? So remember the standard form of a quadratic, right? So at the standard form of a quadratic, we had to, just got a notification here. Okay, it's okay. It's not until 2. 1 your time. Okay, get it out of here. Dink. All right. So we had to rearrange our quadratics into standard form, right? It took a lot more work. What we're going to find with sine and cosine is, although we want them in this very particular form, right? Let's call it the standard form. We can call it the standard form. We have to pull out this k, for example. Notice if you compare the sine one and the cosine one, the only difference here is that this is sine and this is cosine, but a is the same, k is the same, x is the same, and minus b is the same. So what we learned here is that the amplitude, remember the amplitude is the height of one of these bumps, the amplitude is the absolute value of A. So A gets pulled, depending on if you've got a sine curve or a cosine curve, that's just going to determine where your starting point is, right? So sine or cos determine where your starting point is. Yeah. If you have a sine, then you know you start at 0, 0. If you've got cos, you know you start at 0, 1, right? And then you go, go, go. So the amplitude is the absolute value of A. The period, which is the distance it takes to finish one cycle, is 2 pi over k. 2 pi over this value that you've probably pulled outside. Yeah? It's all still inside the sine though, or the cosine. And then the horizontal shift is b from x minus b. So again, we've had this before where if we have something like x plus 2, then b must be negative 2. So let's just write these out. We've got an amplitude is the absolute value of A, right? Which really just means drop the negative. Yeah. We know it's more than that. We know it's a piecewise function, right? If x is greater than 0, then you just have x. If x is less than 0, it's negative x, right? But you can just think, drop the 0. The period is 2 pi over k, and the horizontal shift is b, right? If y is 2 sine 3 times x plus 2, right, b is negative 2. So it would be a shift to the left. All other things that we know about functions and graphing functions that we've talked about still apply, right? So if I take the negative of the function, that flips it over the x-axis, right? So all my y values become negative and flip up if they're negative already, right? So all other properties we know about graphing functions still applies. Still apply, right? For example, if f of x, what did I want to say here? And I don't even have it. If y is negative f of x, then you flip on the x-axis. And if you have y equals f of x plus, trying to think of a letter, a is taken, b is taken, plus c, right? Move up c, right? Then you just shift everything up by c. So those things still apply, and we're gonna kind of ignore them because we're gonna do our graphing in Desmos, but it's good to keep in mind and say, oh, that's why it looks weird. It's because I flipped on the x-axis, for example, right? So we still need to keep it in mind, but it's not something I'm gonna hound you on. What I need you to know is, given a function, are you able to tell me what the amplitude is, what the period is, and what the horizontal shift is? And then tell me how it would affect the graph. So let's do, Yeah, let's do just one of these where we don't have any horizontal shifts yet. And use Desmos to check your work. Okay. So we're going to find the amplitude and the period of one of these functions. So let's do 24. Okay. 24 says that y is the -3 sine 6x. Okay. So what I need to do is I need to rewrite this or this. I know I have a sine function, which tells me a lot of things, right? It tells me I start at 0, 0. It tells me that I need it to look like this. Right, so I need it to look something like this. So what I'm going to do is I'm going to rewrite my function to match this. Right? The only thing that's missing is that I don't have an explicit x minus b, but that's okay. I can rewrite it and say y is -3 sine 6 times x minus 0. I can expand the 6 inside. 6x minus 6 times 0 is -0, so it's the same, right? Notice that all of this is inside the sine function. All this is inside sine, right? Which we'll need to use when we're graphing. Which we need to keep in mind when typing into Desmos. Okay, so here, just rewriting, if I have y equals -3 sine 6 times x minus 0, let's just highlight here. I've got a is -3, right? Just matching now. I've got k is 6 and b is 0, right? So now if I'm asked to find the amplitude, the period, and the horizontal shift, I guess there was no horizontal shift. That's okay, doesn't matter. Nice to have some practice. So the amplitude is the absolute value of a, which is the absolute value of -3, which is just 3. What does that tell me? It tells me that the height of this thing from the x-axis is going to be 3. Height from the x-axis is plus minus 3, right? Up 3 or down 3, right? Total distance of 6 in these loops, right? The period is 2 pi over k, which in our case is 2 pi over 6, which would be pi over 3. Okay. One really common mistake is you just think the 6 is the period, but no. 2 pi over k is the period. So you have to do that little bit of math to figure out what the period is. So now what that means is that it only takes a distance of pi over 3 to squeeze a whole cycle in. A whole cycle happens in a distance of pi over 3. What does that mean? It means that you have to go up and down and up again in a shorter distance. So this thing is going to be smushed together. And then my horizontal shift which is B, which is 0. So there's no movement to the left or to the right. No movement left or right. Right. We've got a negative here, okay? We're just kind of ignoring it. We found our amplitude, but if you remember, right, if we take the negative of a function, it flips it on the x-axis, right? So here, I'll just write, oops. Flips on the x-axis. So we know things like, we know where we start at 0, 0, and then instead of heading up, we're actually heading down, right? Because it's flipped, so it's gone like this. And then I've got this stretched out, but also smushed together graph. So let's graph this in Desmos. And what I'm gonna do is I'm gonna graph the original, and just like we did with the quadratics, just to check our work, I'm gonna graph this one that I've written out or rewritten. Right? It's not that changed, so it should be okay. But let's try it in Desmos. Where was it? Okay, it was -3 sine. So the sine and cosine tangent, it's even got fancy things like the cosecant and the secant and the cotangent, but just ignore that. Sine. And then because everything has to stay inside the functions, right, I've got 6, I think it was 6x and bracket. Let me just make sure that that's what it was. -3 sine 6x. Okay. Notice what we said here, right? All of this 6 times x minus 1 has to stay inside the sign. So how you're going to do that in Desmos is, if you want to check your work, right, you've got -3 sine, and then another bracket 6 end bracket, another bracket x minus 0 end bracket, end bracket. These should be the same because I haven't changed anything. Okay, so now let's just go try to zoom in here. Starts at 0, 0. Remember, it's been flipped on the x-axis, we knew that. And then it went down to -3, pi over 12, -3. Okay, pi over 6, and then let's see if I can go up here, up to 3, pi over 4, and then a whole cycle happened in a distance of pi over 3. So it looks good, right? We started here at 0, 0, and then we got to pi over 3, and the whole cycle's in there. But if you kind of zoom out, right, it's all smushed together and stretched out. Okay. So let's see here. Let's do another example. So a lot of these first ones are pretty basic. Let's do 40 together. It's a little bit weird. It's one of the first ones where we have something attached to the x, right? So what we'll need to do is we'll need to rearrange this and pull out the common 2 over 3. So let's do 40 first. Y equals 2 sine 2 over 3 x minus pi over 6. Okay. So here we want it to match this again, so I'm going to copy so I have something to look at here. To match this, right, with the x alone, I need to pull out, so whatever is attached to the x is what I have to pull out. I have to pull out that 2/3. So I need to pull out a common 2/3 from 2/3x, easy enough, but also pi/6. So to match this, we need to pull or factor out, I should say. We need to factor out a common 2/3. So from 2/3x minus pi/6, and maybe I'll write out the whole function, y equals 2 sine of this. Okay. So what I need to do is I really need to do pi/6 divided by 2/3, right? Pulling out a common. So pi/6 divided by 2/3, fraction over a fraction, we know what to do there. Pi/6 times 3/2. This is going to become pi/4, right? 3 and 6 are going to cancel to make 2. 2 times 2 is 4. Oops, change it to that color, which is pi/4. Okay. So what that means is that you can rewrite this. You can rewrite it as 2 sine 2/3x minus 2/3 pi/4. And you can check it, right? 2 pi/12, that's pi/6, right? Which is what we had. So now I can pull this 2/3 outside, still inside the sign, right? So I get 2 sine 2/3 times x minus pi/4. So now I've got it matching this setup, right? Where a is 2, k is 2/3, and b is pi/4. K is 2/3 and b is pi/4. Great. Now we can set up, okay, we can find the amplitude, we can find the period, and we can find the horizontal shift, and then we can have a pretty good idea of what this thing looks like, what this graph is supposed to look like. So the amplitude is the absolute value of a, which is the absolute value of 2, which is just 2. The period is 2 pi divided by k. I'll put that in first. Oops. Which is 2 pi divided by 2/3. Remember, this is essentially just a fraction over a fraction. So you've got 2 pi/1 times 2/3 gets flipped, 3/2. 2 and 2 are going to cancel. So I get a period of 3 pi. Thinking about our regular, is this a sine function? Yeah, our regular sine function has a period of 2 pi. So now it's being extended to 3 pi. So it's going to take a little bit longer to finish a whole cycle, right? But it's also stretched out. Instead of an amplitude of 1, it's got an amplitude of 2.
Emily?
And then, yeah.
Like, do we need to put the value of pi, or is it just like that?
In here, do you mean?
Yeah.
Yeah, so you need to keep the pi.
Oh, okay. So no need to put the values, right?
No, just
Okay.
keep pi.
Oh, okay. Thank you.
Yeah, good. So then the horizontal shift is b, which is going to be pi/4. And because it's positive, it's a shift to the right. Shift to the right. So knowing that sine starts at 0, 0, right? Then if I have to shift this to the right, I'm actually starting at pi over 4, 0. And then it takes me a distance of 3 pi to do a complete cycle, right? And so what this thing looks like is here, this is our usual starting point, start point for sine. Okay. But now we've shifted to the right to pi over 4. So this is our new start point. And then knowing the kind of general shape of sine, right, it goes up. There's no flip in this case. There's no movement up and down. So it looks like it's just going to go up. So from here, it's going to go up. We've got an amplitude of 2. So at this point, we've got 2 and -2, let's say. So it's going to go there. And then this distance from here to here is a distance of 3 pi, right? So it's 3 pi from pi over 4. Which is your new starting point, right, from here. Okay. So from 0 to 3 pi, you wouldn't quite finish, but remember you've moved your starting point, so, and then you add 3 pi. It's a little bit tricky, you'd have to, so to figure out where these points actually are, you'd have to divide 3 pi up into quarters, and then go from there, but I don't want you to waste time doing that, so we're just gonna draw it in Desmos. What I'm gonna do is I'm gonna draw this, this original function as well as my second function that I kind of got to myself, make sure that they're the same, otherwise I've done something wrong. Okay, get rid of these ones. So it was 2 and then sine. Hopefully, oh yeah, I've got them here. And then remember, you're going to do everything inside the sine with brackets. So 2 over 3, close those brackets, and then x minus pi over 6. Remember, there's a pi button down in the left-hand corner there beside the square root. Pi divided by 6. And those brackets, well, there's an extra set of brackets here, there, and those brackets. Okay. So like I said, right, we've got this shift of, wait a second. 2 pi, 2 sine, 2 over 3. Oh. Because I actually, there. I did a combination of the first one and the second one. That's not what I wanted to do. Here, pi over 4, that's the horizontal shift, right? And then it takes me from pi over 4 to 13 pi over 4, which should work out to a distance of 3 pi to go through a whole cycle. Now I'm going to do that one that I worked out myself. 2 sine, and it should be the same. Now I'm going to put 2 over 3 in brackets. Oops. Step it out. X minus pi over 4. Oops. Divide. Oops. Better to start over sometimes. Good. So now we see that these two graphs are exactly the same. That's a good thing. Because here, right, I have all my cutoff points. I have an amplitude of 2, right? It goes up as high as 2 and down as low as -2 on the y-axis. I've got a distance of 3 pi to cover an entire cycle. Everything's been shifted over to the right by pi over 4. So let's do another one of these before we move on. Let's do 42. Because it's got cosine and it's got a shift up. Might be nice to see. So we've got y is 1 plus cos of 3x. I've got it on the side here for graphing pi plus pi over 2. Okay. So here, right, we're going to notice, oops. Shift whole graph up 1. Okay, so the whole graph of cosine is going to get shifted up 1, but first we're going to figure out what the amplitude and the period and the horizontal shift is. So to get this, so I'm going to ignore the 1 plus for a second, and I'm just going to work on this cosine. Okay, so I need it to look like this one. Right, I need that to look like that. So again, I've got this 3x, but I'm only allowed to have x on its own. So that means I need to pull out a common 3 from both 3x and pi over 2. Okay. So this becomes y equals 1 plus the cosine of 3x plus pi over 2, which is going to get split in, and I'm just going to do this work on the side here. Pi over 2 divided by 3 over 1, essentially, is pi over 2 times 1 over 3, which is pi over 6. Okay. So this we can rewrite as 3 times pi over 6. 3 pi over 6 is pi over 2, so that's good. So that's safe. Now I can pull out this common 3 outside, and so I get y is 1 plus the cosine of 3 times x plus pi over 6. Okay. So here, let's see. A is 1, K is 3, and B, it's x plus pi over 6, so B must be negative pi over 6, which means it must be a shift to the left of pi over 6. So our amplitude is the absolute value of A, which is 1. The period is 2 pi over k, which in our case is 2 pi over 3. Okay. So it's going to take a distance of 2 pi over 3 to cover a whole cycle. And then the horizontal shift is negative pi over 6, which, because it's negative, it's to the left. So there are a few things that we know. We know cosine starts at 0, 1, right? So it starts up here at 1. And then, but now I'm shifting over negative pi over 6. So I'm shifting over into the negative x's pi over 6. And then I'm moving this whole thing up 1. Okay, so what happens is if you've got your original starting point for cosine, which is here, start point for cos, right? Then if I shift to the left, I get to negative pi over 6, 1. So I shift left 1. That's my first step. Shift left pi over 6. And then I go up 1, which puts me at negative pi over 6, 2. Cosine starts at 1, 0, and then it goes down, right? Because it starts up at the top, so it has to go down, it can't go up. So then, and there's no flipping going on here, there's no negative cosine, so it's just gonna go from this point, it's gonna go down, and then it's gonna go back up. And what's gonna happen is it's all gonna, one cycle is gonna happen in a distance of 2 pi over 3, right? So at negative pi over 6 plus 2 pi over 3, everything's gonna happen in that distance. Right, so let's see what it looks like in Desmos. Again, I'm going to graph the first one that I was given, that function, as well as the one that I worked out on my own, just to make sure they're the same. So we have 1 plus function cosine 3x plus pi over 2. That's the function I was given. Why is it doing that? Oh, because I didn't do an x, 3x, there. Let's make sure that the function that we, when we pulled out that common 3, that we actually ended up at the same thing. So 1 plus, and again, the cosine of 3 times x plus pi divided by 6. And bracket and bracket. Oops, one too many brackets. Okay, so it looks like they're overlapping. That's good news. It means I did it right. And let's just see here. So starting up here, just like we thought, negative pi over 6, and then it's going to take a distance of, what was our period? 2 pi over 3. Negative pi over 6 plus 2 pi over 3. If you did it, you would end up at pi over 2. Right, and so like we said, it's going to trace down here. Oh, don't know if you can see my pointer, or trying to trace on here. There. So it's going to start up here, and then it's going to go down, and then it's going to dip back up. And here, now I'm repeating the cycle once more. Right, so I've gone a distance of 2 pi over 3. My amplitude is 1, right? But then I shifted up 1. Yeah. Good. So graphing trig functions, not that bad, as long as we know how to find the amplitude, the period, and the horizontal shift. And then the rest is just kind of follows from just regular graphing of functions. Okay, so let's see here. Okay, we're going to start 6.1. It's nothing new. So in chapter 6, what happens is we just do everything we did in chapter 5 again, but we just start calling things angles, right? And so the tricky part, let me just find a new page here. 6.1, I think it's called angle measures. But let me just confirm. Oh yeah, angle. Sure, measure. Okay, so what happens is we've seen something like this, right? All we're missing is the unit circle. But other than that, everything's kind of stays the same. So let's talk about radians. We've talked about radians in the sense that we need to be in radian mode when we're using our calculator. Okay. And I'll bring in the graphic as well. Okay. So if we're talking about a circle, a unit circle, so a circle of radius 1 is drawn with a vertex at its center, okay, that's very much like what we've been doing, right? We have been going like this, right, to draw our unit circle. It's the same. Then the measure of this angle in radians is the length of the arc that subtends the angle. So remember how we said, okay, let's see here. Oh, now I drew it all crooked. That's okay. So if the length of this side is the same as this angle, remember how I said, oh, actually, this pi over 6 here is actually going to be an angle, right? So what happens is if you've got pi over 6, this is actually the distance here, but it's actually it's also going to be this angle, pi over 6, right? And so that's how radians behave. The radians are the distance on the curve, right? Or on this unit circle. So we've already talked about angles in radians. This means we have already talked about angles in radians, right? And some other common ones that we know are pi over 6, pi over 4, pi over 3, pi over 2, and then the quarter wave marks for sure, right? So let's bring in this example here. Not really an example, but something to look at. 1 radian, kind of hard to think about, right? But the easier ones to think of now, because we're so used to the unit circle, is that, okay, well, this distance I know is pi. So what that means is that this angles we usually denote by kind of going from here to here. This angle is pi. This angle is pi over 2. We're going to start talking about degrees and the relationship between radians and degrees. And so we know that this distance is 180 degrees. So that means 180 degrees is pi. Pi over 2 must be 90 degrees, right? And so even a distance like 2 radians, even though there's no pi and there's no obvious cutoff point, we can figure out what it is, because here, pi over 2 is just a number. Pi divided by 2 on your calculator is roughly 1.57, right? So here you're at 1.57, so you'd go a little bit further. That must be a distance of 2 on the unit circle. Okay. So radians are just taking that distance from the arc and making it an angle instead. They're the same. So let's talk about the relationship. So we should be able to move back and forth between radians and degrees. So we said 180 degrees, which we saw up here, right, is the same as pi radians. Usually if there are no units, right, we don't usually have radians. We just leave it blank, right? So pi is in radians because there are no units. 1 radian must be 180 over pi degrees. That's hard to think about, right? But what happened here is you just divided pi over here, right? 1 degree then must be pi over 180, right? So just moving the 180 over here and kind of holding the degrees and the radians steady. Now that's hard, so I actually prefer to just read it like this. To convert degrees to radians, multiply by pi over 80 or 180. To convert radians to degrees, multiply by 180 over pi, right? So I actually just keep track of these. Sometimes it's useful to have these conversions here, but I find them confusing. So you've got them, but you don't have to use them. So here, let's see. We'll do some conversions, mostly from radians to degrees. And just because degrees are more familiar, probably. If I tell you, oh, I make a 90-degree turn, you know it's like this, boom, boom, right? 180, boom, 360, full circle, right? So we know a lot of degrees already. So if we have to find the degree of an angle, let's remember some things. A negative angle just means that you're going in the clockwise direction instead of the counterclockwise direction. And what else? What else? Which one do we want to do? Maybe we want to do 5 pi over 6. Let's do 19. So we've got 5 pi over 6, no units, means we're in radians. So to convert radians to degrees, we just multiply by 180 over pi. So I'm going to use the different colors, times 180 over pi. Notice that the pi's are going to cancel. What I'm going to do is I'm going to see if 180 is divisible by 6. 5 is not divisible by 6, but maybe 180 is, and then I can simplify it a little bit. 180 divided by 6 is 30. So what I get is I get 5 times 30, because 180 divided by 6 is 30. Times 5 is 150. 150 degrees. Okay. Only degree measures need units. Right? If there are no units, it means it's in radians. So depending on if you're in degrees, you're working with degrees, or if you're working with radians, you'll have to change the mode on your calculator, right? So on this one, I've got a little DRG up at the top. I don't know, it's kind of hidden there. But you'll want to make sure that you can move from radians to degrees and back and forth. Let's do another one. Let's do 28. Negative 13 pi over 12. No units, so it must be in radians. To convert to degrees, though, I need to multiply by 180 over pi. So times 180 over pi. Notice that the pi's are going to cancel again. And then the 180, let's just see if it's divisible by 12. 180 divided by 12 is 15. So this becomes negative 13 times 15, which is negative 195. The negative, right, tells you to move clockwise instead of counterclockwise. That's going to be the same, and I forgot my degrees here. That's going to be the same for radians and degrees. So here, move clockwise. Okay, good. So just moving between radians and degrees, not bad. All right, let's talk about standard position, coterminal, and then we'll leave the rest of these for next day. Oops. Copy that. So when we start here on this x-axis, that's what we've been doing this whole time, right? And so what we're saying is we're going to start on the x-axis, and then we're going to do measure our angle from there. That's what we call standard position. So when we start on the positive x-axis and measure our angle from there, we say the angle is in standard position. We say the angle is in standard position. Okay. Another thing to note is that if you look at A and then you look at C, even though we've gone around the circle once, it looks like these end up at the same place, right? Since A and C end in the same position, we say that they are coterminal. Okay, meaning the terminal is the end, right? And so they're coterminal, they end at the same position. Since A and C end in the same position, we say they are coterminal. And that's good for today. So have a breeze through the rest of those notes, and we'll keep working on them next day and just kind of wrap up. Are there any questions?
Emily,
Stop this recording. Yeah?
I just got one question. Like, we are doing the professor's survey.
Oh, okay.
Yeah, like, do we need to do yours as well?
I haven't heard anything about it. Usually they let me know if I have to get them done.
Like
So
it's
I don't think they're doing mine this term.
oh, okay. Means like it's just like on the bottom of every like on the bottom of the Moodle.
Oh.
Like we just need to fill our professor's name, choose the course number, and then just click on the survey.
Oh, okay. So if there's an option to do it, but I didn't know it existed.
Yeah,
So you
like
don't have to.
my other professors, they are all saying to complete that.
Oh, maybe I should be paying more attention.
Mm.
When does it close?
I think after the exams or like the
Oh, okay.
when the
I'll
semester.
have a look and see if I have to have mine done, and then I'll let you guys know on Thursday if I need you to do them.
Yeah, sure.
Yes, and if you could also send the link for the place to go to, because on the evaluation thing, your name is not there. So I don't know how that works.
Oh, so maybe I don't have to, like, they usually don't make everyone do it. So they'll like pick people every term. So I think maybe I wasn't picked. Because if it's not an option, I'll look into it and let you guys know on Thursday. How about?
Yeah, sure.
Cool.
Thank you.
Awesome.